We're learning about and learning to use a numerical method called the trapezoidal rule. So let's just jot that down. It's a numerical method, and they're often used in mathematics to estimate. Sometimes it's a good estimate too. So it's a numerical method, and you may have learned, or you might be in the process of learning through integration, that integration provides, one of the applications of it anyway, provides the area under a curve. So we have a link there with area under a curve, which has a lot of applications, both theoretical and practical. So the trapezoidal rule is a way of essentially using numerical methods. So it's not actually using integral calculus. But it does the same job. It's not using integral calculus in the way you've probably learned already. Okay, so not. But does the same job. So when we do use integral calculus, using the integral to find the area, so it's basically an application of definite integration, which hopefully you've learned already if you're watching this video. If not, hopefully you'll learn it soon, because these go together. They help each other make meaning. So that'll be the area under a curve. In this case here in the light blue, that'll be between x equals a and x equals b. So it's bounded by ordinate lines x equals a, and the other one is x equals b. So that's true for integral calculus, definite integration, area under a curve, and it's also true for this numerical method called the trapezoidal rule. Now let's revise what a trapezium is first of all. Now, trapezium is a quadrilateral, and it's a quadrilateral that has two sides that are parallel, like those, and the other two sides are not parallel. It has a perpendicular height h between the two parallel lines, and we call the length of one of the parallel lines a, and the length of the other one we call b. And we can use a formula you may have seen. Area, or it might just be called capital A, is basically the average of a and b, so half a plus b, it's just using the mean of a and b, multiplied by the perpendicular height h. That is not a slant height, it's a perpendicular height, and that's the area of a trapezium. So the trapezia that we use with this often look a bit like this. They'll go up vertically, and they'll have their two, sorry, that should be horizontal, and they'll have their two parallel lines, and the lines moving from left to right, they're the ones that are not parallel to each other, so it's standing up on its end as such. With that bottom part, usually that's horizontal in orientation. Why do we use these numerical methods anyway? Because if we know how to integrate, well, can't we just do that? Well, sometimes we might not know how to integrate. Okay, we might have a function, we don't know how to integrate it, perhaps it can't be integrated for some reason. The other thing is that sometimes there is no available function, it's not defined, or it cannot be a situation, a curve cannot be represented by a function. So there are purposes for numerical integration. The calculations are easy to do, but they can be long and tedious, and it depends on things like the number of strips and the type of function, if you're using one, the substitution, and so on, the evaluation. So there's got pluses and minuses. The more strips you do, the more accurate. So more strips, more trapezia. Okay, so we're gonna call these trapezia strips. More strips gives more accuracy. But of course, therein lies more work and more time. And if we have more strips means narrower strips. And that links to the idea that we explore more in another video, is that the area under a curve using integration is the limit of a sum. So you can see there's a kind of a relationship there. We'll be looking at that in a different video. The limit of a sum of strips, I suppose. Okay, the areas of all of these strips. If you took the ultimate limit, which would mean they get infinitely narrow, using loose terminology, which means there has to be infinitely many, the limit of that using limits, which is, you've seen that with the prefix lim from your previous studies, the limit of a sum of those will give the true integral area under a curve using definite integration. So this is a numerical method for estimation. Okay, let's have a look at the formula. So what we do is, for some given curve, we've got those ordinate lines, the boundaries, the vertical boundaries, as I mentioned before, between x equals a and x equals b. And we've got something that might look a little bit like left-hand rectangles, right-hand rectangles rule, center rectangle. Okay, there's some similarities, but we're not using rectangles, we're using trapezia. And you can see the trapezia here. Here's an example. So there's one trapezium there. Whoops, that should be horizontal, as I said before. And you can see the top there. Now that at that particular interval it misses the curve, so you can see one example of where we might see some error. And it's just like with these methods you've seen previously, it can over or underestimate a certain area. As we make the strip width, which by the way is W, you need to know that, W. As that gets narrower and narrower, we need more and more strips, but the accuracy tends to improve a great deal. So the formula comes from adding all of these trapezia areas together, and so you can see down the bottom of your screen we've got a way of putting it together. So f of x0 is when we put in the x value here in line with that spot there, which is the same as a. Okay, and we've got basically sub that into the function given, if there is a given function, plus the next one, f of x1, and divide that by 2 and then multiply that by h. Now h is the strip width. Now remember just a moment ago when I had the generic trapezium, okay, we had that, oh, sorry about the curve there. We didn't quite have that. I've just straightened up this left hand side, and because it aligns better with what we're doing on the function. But the main thing is that two of the sides are parallel, A and B. Okay, they're the two parallel sides. We had that there just a moment ago, and we've got H. Now H gets replaced by W later on because it's not really important, it's just a symbol really, but it looks like H on our generic diagram over here, but once we turn the strip so that it's sitting like, oh dear, I keep drawing a curve there. Apologies. Thanks for your patience, everyone. Terrible, having stylus issues. But basically that H is now sitting across there. Well, why not call it width? Okay, so later on you'll see the H go and it'll be replaced by width, but it's the same thing. And so basically you can see that we're really just subbing values into a formula, and we're doing it over and over again, and it depends on how many strips we've got, okay, and hence the ellipse points there. And we go up to x sub n, which corresponds with our boundary b there for the x value. So like you saw for rectangular methods, we're subbing values into a function quite a lot. Now what you can do then is tidy all that up. It's interesting to note that we get multiple numbers of certain things. So we've got a common factor, first of all, of h over 2. Okay, and we can factorize that value out there. We have one lot of f of x naught, but we have two lots of everything else except for f of xn. And so we can, those ones that there's only one of, we can separate them there. And all of the others have a common factor of 2. So we can group that sum over here. And what we end up with is h over 2 multiplied by the first ordinate. Now the ordinates are when you sub the first ordinate is when you sub x naught into the function. The last ordinate is when you sub xn into the function, corresponding there and there. And there's 2 times the sum of all the middle ordinates. So they're all the others that are in between the first and the last. And we can make that a bit slicker. Let's have a look at the slickened version. Slickened version is here. So what we do, we write the integral between a and b, which is the area under the curve for a given function, is approximately equal to what we just saw then. Now the difference is that the h has been replaced with a w, and that approximation equals this here. If you're going straight from here to here, you should use approximately equal to signs, the wavy ones, or possibly you could use that symbol. Now, it basically is a half w outside of e plus 2m. We need to know what these are. So w is the strip width, alright, and sometimes we have to work w out, and I'll show you that in an example in just a moment. So w is the strip width, and they're all equal width, as you would have ascertained, certainly by now. And E is the sum of the end ordinates. So it's the sum of the first one, if it's called f of a0, plus the last one. Alright, so that's what E is. It's the sum of two things. And M is the sum of all the middle ones. And then that once we've identified E plus M, we have to, like we saw just before, we have to double M. And then once we calculate all that, we have got our approximation for an area under a curve using the trapezium rule. Starting with a fairly easy one, and look, a lot of people could just do this with definite integration, but we're going to start with an easy one, okay? So maybe you wouldn't use a trapezoidal rule on this one, but this will show that you get a pretty close answer to the true answer. So as a touchstone, I've just calculated the true area. It's going to be 60 units squared, and let's see how close we go. So what you do first, it's always good to, even if the question doesn't tell you to, sketch the graph. Do that first. Now, easy questions might tell you how many strips to divide something in, and they may even give you a width. But if you don't know those things, if you only know, let's say, the number of strips or number of intervals, how do you work out h, the strip width, or w? Okay, so we can call that w. Well, using a little bit of direct logic, the entire width is between 1 and 4. So that's 3. To get that 3, of course, you go for minus 1. So that was called B, that was called A. So to get the strip width, W, if they didn't tell you to use 0.5, you would go B minus A over the number of strips, which is N. So it might be handy to copy that down. It's just from a bit of direct reasoning. So B minus A over N will give you the strip width. It's up to you a lot of the time to determine that yourself. Okay, so I've written down my formula. The integral is approximately equal to W over 2 outside of E plus 2M. And yep, and that checks out. It tells us there in the question as 0.5, but if it didn't tell you, 4 minus 1 is 3, and there's six intervals or 6 strips, and that's 3 over 6 or a half. Okay, so the strip width is a half, so that's a half over 2, which is a quarter. Half of a half. E, well, we need to work out what E is first. So f of 1 plus f of 4 will give us E. Alright, remember we're just substituting 4 and 1 into the given, sorry, wrong one, this one, the given equation. Alright, so 3 by 1 squared is 3, minus 1 is 2, and 4 squared is 16, 16 by 3 is 48, and 48 take 1 is 47, so we have 2 plus 47 is 49. So we've got E. Now taking care to get these ordinates for M, so we've got to work out what M is first, and then we'll double it. So M, we've got here down the bottom left of your screen, that's 1.5 or 1.5, that's 2.5 or 2.5, 3.5 there. Okay, now the middle ordinates are the ones excluding the end ordinates. We've already looked at them, they're E. The M's are going to be these other ones correspondingly here. So we've got f of 1.5 plus f of 2 plus f of 2.5 and so on, as you can see there. Then we just have to evaluate those by summing it into 3x squared minus 1, and we get the following as such there. And then the last step then is to add that to get M. So M comes out as 96.25, and you may even wish to work out 2M while you're at it, which is 192.5. We just multiply it by 2. It's time to sub those into the equation now. And so it's E, which was 49, plus 2M, which is 192.5, and add those together, then multiply it by a quarter. The final answer is 60.375 units squared, as it is an area, compared to when we had our true value, which was 60, so 60 versus 60.375. So the amount of error was 0.375 units squared. So one way of getting a percentage error, which is something you often have to do, is to look at what we got for the estimate, which was using the trapezoidal rule, minus the true value, which was 60, and divide it by the true value, and then times that by 100 to convert it to a percentage. Let's do that. So notice how the top has the absolute value symbols around it. So if it's negative, it comes out as positive. Okay, depending on whether it over or underestimates it. That just drops the negative sign if there is one, essentially. I've already done that there. The error is 0.375, and whether it's above or below. And we have 0.375 over the true value using definite integrals was 60, and we times that by 100 to convert it to a percentage, and it should come out nice and small. Let's have a look at what that is. Okay, so I get 0.625%. That's less than 1%. Okay, it's not 62.5%, that's 0.625 of 1%. So that's a very small error in the area calculation. So that one worked quite well. And I think what helped there was that there were 6 strips, and yeah, that's not a bad number of strips for that sort of function.